Hello. Okay, nice seeing you. I confirm that what Vivo has just said is entirely true and nothing but the truth. How many of you tonight are developers? Okay. To make a disclaimer, by the end of this talk, the non-developers in this audience will be bored to death. So I disclaim any responsibility for your mental and physical state at the end of this lecture. You've been warned. Okay, so let me not stand in front of the projector. First thing first, for those of you who are not quite familiar what Chrome OS is, a quick introduction. First, again, I don't work for Google, so that's okay. This is Google's take at a very thin web client and their way to run Chrome in a dedicated environment. Now, that all started back in 2011, and at that time, Google decided to sort of branch Gentoo and start from that, add some nice security through SE Linux, and also emphasize on performance. Why? Because they really wanted the best possible performance for their browser. Now, another special thing about Chrome OS is that it is architecture agnostic. That means that unlike Windows, which is very much x86-centric, or was up until lately, and unlike Mac OS, which so far, I mean, they switch architectures now and then, but once they switch an architecture, they stay with it. Chrome OS is architecture agnostic, and they run on several architectures, x86, ARM, and there have been some unofficial ports to MIPS. Chrome OS is largely open source, and once you remove the closed parts from Chrome OS, you get Chromium OS, which is everybody who is skilled in building large Linux projects could actually clone their repo and build the operating system for themselves. Another thing about Chrome OS is that it's an open platform, so any vendor of hardware can actually start making and selling their Chrome OS devices, which is actually good for the purpose of this talk. So they can do that as long as they comply with Google's very rigid requirements for the operating system. Another thing, recently when Linus Torvalds himself was interviewed, and the interviewer asked him, is there such a thing as a popular consumer desktop Linux? Actually, Linus gave an answer that Chrome OS pretty much is that consumer desktop Linux. So yes, there is such a thing as a consumer desktop Linux, and this is Chrome OS. And now the final two bullet points on that slide have the most relevance to this talk. They have to do with the fact that back in 2014, Google introduced support for Android apps. At first, they introduced support for a couple of apps that they needed, that they deemed important in Chrome OS, and later on, by 2016, they introduced support for pretty much every app on the Android App Store. That means that users could just download applications from the Android App Store, and they would run in Chrome OS. Now, what's the relevance of that to this talk? The relevance of that to this talk is that those of you who have any experience in Android would know that Android actually relies on OpenGL ES as its core API for games and other things. And this is where we step in. So how does Chrome OS actually do that? There is basically a software compatibility layer that goes under the name of ARC, Application Runtime for Chrome. And back in 2016, at an event known as XDC, or XORG Development Conference, there is a very good paper on ARC and how it makes Android applications run on Chrome OS. Actually, this paper is very important and one of the main sources of credible information that I've used throughout to get my results. So basically, ARC is a compatibility layer. So if one wanted to do any development work on a Chrome OS, what would they do? Apparently, since there is support for Android applications, they could go to the Android store and download some of the self-hosted Android IDs. That would give them some kind of an editor, that would give them some kind of a toolchain, compiler, maybe even a debugger, who knows. Frankly, I'm not an Android developer, so I'm not the person you would turn to ask for the best Android IDs. But even if I was, I would still prefer to do my development on the Linux environment because of the rich choice of toolchains and development tools. Now, since revision 70, Chrome OS supports something which is basically Debian or any other Linux, for that matter, in a virtual machine. So basically, you can get pretty much any standard distro application running in a virtual machine on Chrome OS. Now, what is the problem with that? The problem is that so far there is no support for a virtual GPU in that virtual box. So if you want to do graphics development, and in this particular case OpenGL, you're in the cold for now. So the next option is Chrome OS developer mode. There is something in Chrome OS called developer mode, and in essence, it relaxes the security of the operating system and gives the user pretty much full access to the underlying file system. Well, not completely full, but pretty good for the purposes of our purposes. Now, once we have such an access to the file system, we could do several things. One of them is install Crouton. Crouton is just a root environment that allows users to install most Linux distros user spaces on top of Chrome OS. And so basically you have a complete Linux distro in your Chromebook. What are the pluses and what are the minuses of that? The pluses of that are that you can have your favorite distro. The minuses of that is that this pretty much runs only on Intel Chromebooks, because most current Linux distros rely on open source OpenGL drivers, usually in the form of MessageGL. And those Chromebooks that don't have Intel GPUs, so pretty much every Chromebook with an ARM or Imagination Technologies or somebody else's GPU, they're again out in the cold. And the last option, actually, not to try to do any abstraction layers like we have been trying to do so far, but do development natively in developer mode on Chrome OS. Actually, you can do that because Chrome OS gives you access to the file system, and some pretty good folks at an open source project called Chromebrew, like Homebrew, but Chromebrew, have actually provided a bunch of a great selection of most useful Linux packages and toolchains that you would find in a normal Linux distro. So basically, what you get with Chromebrew on a native development mode Chrome OS is something that very, very much resembles a normal Linux desktop. So what are the pluses of that? The pluses of that is that because Chrome OS supports Android applications, on every Chromebook natively out of the factory, there's OpenGL pre-installed, an OpenGL software stack pre-installed functional to the standards of Google, which is good. So how do we know that there is a software stack that implements OpenGLES? How do we tell that? Well, we start searching for its components in the file system of the operating system. So first thing first, we should have a component that interfaces us or allows user space applications to interface to the DRM or direct rendering manager of the kernel. So if we look in Chrome OS under that path, /user usr/lib/libdrm. SO is a typical library file that provides interfacing to this kernel component. So we have that component. That's good. Next, we'll look for something that provides native binding to GLES contexts. And that, again, can be found under Chrome OS in the same location, exact same location. And this is the EGL API. Those of you who are familiar with OpenGL are very much likely users of EGL in one form or another. And finally, we need the actual OpenGLES library that allows us to do the API calls. And that thing is usually found for OpenGL 2.0 and above. It's usually found in a library which is called libgles version 2. And again, that can be found in the file system of Chrome OS in a system folder. So we have 3 key components that are found in Chrome OS that would potentially allow us to do OpenGL natively on Chrome OS. Now there is one last thing there. Somehow, once we start rendering with OpenGL, we would like to show things on screen. And because it's a pretty new environment for us, we don't really have an idea at this stage how to show frame buffers on screen. But we'll get to that later. Now, before we even attempt to do anything with OpenGL on a Chrome OS, we have to make sure that the DRM layer in the kernel supports one piece of functionality that is crucial to our purposes, and this is render nodes. So render nodes in DRM lingo means that an application can have non-exclusive access to the device that corresponds to the GPU. And lo and behold, in that paper from XDC 2016, there is a page that basically says that Chrome, that is the browser, the main application of the operating system, is the DRM master, but any Android application is not a DRM master, does not need to be a DRM master because it uses render nodes. And this is exactly what we need to do to get results on this operating system. So, hey, so we have a chance to get OpenGL running here. Okay, phase 1. So once we have all the necessary software pieces, we start to prod the GPU and see what happens. So by pinging the GPU here, these are the 6 basic steps that we need to take in order to see whether we have a functional GPU or not. We need to establish an EGL connection to the display server or whatever runs there. We need to enumerate all pbuffer EGL configs. Now, what is a pbuffer? For those familiar with OpenGL, they would know that pbuffer just means an off-screen bitmap that the GPU can render to. It basically stands for pixel buffer. So we enumerate all pbuffer capable EGL configs. Of those, we pick one that we like for some reason. We ask EGL to create a surface from it, from the pbuffer, and then we create an OpenGL2 context that has this pbuffer-based surface set as both draw and read surface. And voila, we have a context that we could try rendering to. We draw something in that context, and then we read back the content of the frame buffer via GL read pixels and see what happened. We save that to some popular file format, and then we see what happened. And this is the first thing that I got out of pinging the OpenGL stack on a Chromebook. I passed down some scene content. In this particular case, that was a stupid polar sphere with a tangent space normal mapping and one phone light. And I got back exactly what I sent to the GPU. So yes, the GPU in a Chromebook can render to an off-screen buffer. Not bad. So, phase 2. Now that we know that the GPU can render something, how do we get that on screen? We cannot work with bitmap images all the time. It's real-time graphics, after all. So how do we show a frame buffer on screen? Again, reading that indispensable source, the ARC paper, we see that actually ARC provides a Wayland manager. How many of you know what Wayland is? Wayland is a display manager that is supposed to be the successor of X, the venerable X in Linux and Unix world. So ARC provides a Wayland protocol to the underlying compositor, and Chromebrew, on its turn, provides libwayland, which is a client-space library for communicating with this server. So good, we have the system component and we have the client-side library that we could try to use. Now, unfortunately, here the story would have ended on most other platforms, because on most other platforms, once you have Wayland and you have EGL and the open libraries, then you just go on and do a Wayland EGL window create, you get a surface that is usable by EGL, and you pass that surface to EGL, and you have a surface that you can work with. Unfortunately, that is not the case with Chrome OS and Arc. Here, actually, the story begins. So first thing first, so we see that the standard way of showing things on screen will not work this time. What do we do next? Well, we could repeat our little trick with the bitmap file and actually read the frame buffer into a shared memory base Wayland buffer and pass that Wayland buffer to a Wayland surface and on to Wayland, the display manager. That should work each and every time. That's a foolproof plan. Now, what's the problem with it? The problem with it is that GL read pixels is an extremely CPU taxing operation. So by just showing a simple frame buffer as big as 1K by 1K and making sure that there are no pixel conversion operations on the fly, we could spend approximately 30 to 40% of a single CPU core just doing the read pixels. Even on a high-end Chromebook, that could take, again, between 10 and 20%, which is just not good. So we could show things on screen, but that's extremely expensive. So reading again that interesting paper from 2016, one could come across the following statement: Wayland interfaces, in addition to the core Wayland protocol, Chromium implements the following interfaces, blah, 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 blah. And at the final line, it says, ZWP Linux DMA buff v1. What the heck that might be? When I read it, I had no idea what that might be, but it sounded delicious in a funny way. Now, by that time, a picture started to clear up in my head, and I said, okay, so I know several things. I know that I can use a pbuffer surface for off-screen rendering, and I know that I need to create a GLES context where I could set the render target via FBO operations to some special image type that potentially I could use to send to the Wayland server. And that special image type should be derived from a Linux DMA buffer object, because there is such a thing as Linux DMA buffer objects. So that sounds like a easy-peasy plan. Now, first thing first, there is such a thing as surfaceless OpenGL ES context. So you can create an OpenGL context without specifying a surface, a draw surface, or a read surface to that context. And this is actually what we want, because we don't have any pre-made surfaces when we create our context. We create a context without any ready surfaces, and we'll get surfaces as we go. So where do those DMA buffer objects come from? How does one get one? First thing, you have to figure out what device from the Linux kernel might provide those buffer objects. And it turns out that there is a device in the system, in the kernel provided file system, that sits under /dev/gri/vgem that does exactly this. You ask it for buffer objects, and it gives you back in return buffer objects. So you get one such dump buffer object from that device, implementing this IO control call to that device. Then you have to promote that buffer object to an actually prime buffer object with a file descriptor using another IO control call to the kernel. And finally, once you have this file descriptor, you can pass this to EGL and ask it for an image object. And you get an image object in return. Once you have an image object in return, you can pass that image object to the GL stack and tell it to use it as a render buffer storage. And voila. You can create your frame buffer objects from that render buffer. Now, what do we do on the Wayland end? On the Wayland end, we have to use that interface that we read about in the ARC document to make sure that it's functional. We get that interface from the Wayland server. We use that interface to create a Wayland buffer from the same prime file descriptor that we used to create our EGL image from. And we use that Wayland buffer as a backing storage to a Wayland surface and pass that to the Wayland compositor. And everything from there on is just standard Wayland frame loop or just a redraw function. At the end of the day, you have this. We have the exact same sphere that we had originally in the off-screen buffer, composite it on the Chrome OS desktop. The good thing is that you can composite it on anything that's in Chrome OS. You can have a video on the background, you can have animations, you can run a browser, whatever, and it composites on top of it. This is kind of neat, as long as you provide the proper alpha channel. So, to stop boring you, what are the conclusions that we can make from this talk? First, the good thing. Chromebooks or entry-level Chromebooks go for as low as $300. So you can get an actual on-the-go development environment for OpenGLES by just spending $300 for an entry-level Chromebook. The ARM models of those Chromebooks actually can give you up to 12 hours of work time, which is pretty great in my eyes. Chrome Brew, on top of Chrome OS developer mode, gives you a very much Linux desktop-like environment. And Chrome OS is truly a consumer-grade Linux, not just by the words of Linus Torvalds, but by anybody's experience. It has blazing fast web, media codecs just work, external displays and extended desktops, and it has a thriving community and the long-time Google support. So everything that has pluses has minuses, of course. So what are the cons? Well, the cons in this case are, because we're using private Google interfaces, Google may change that in each new update. They might scrap things that used to work up to now and introduce new things. Some of those private interfaces in Arc are actually, they claim to be standard Wayland interfaces, but they're not quite standard Wayland interfaces, so you have to be careful. And if you step on a bug there, though, you can report that to Google, and lo and behold, they pay notice. So at those links, you can check everything that I've mentioned so far. There is the Crouton link, there is the Chrome Brew link, and there is the actual demo code that does this. Now, here I was meant to show you a live demo, but for some reason my Chromebook will not talk to the projector over HDMI, so I'll skip the live demo. Yes, it was ironic indeed. Well, that was it. Thanks for your attention.
If there is any questions?
So questions, yes. We have time for questions. Any aspiring OpenGLES developers? Not many.
No questions?
Oh, a couple of questions, yes.
Aren't there any open source libraries that would give you a context on this platform?
No, actually, this is pretty much the first hack of a Chrome OS that gets OpenGL outside of the browser. You can do WebGL in the browser naturally, but this is not WebGL. This is full-blown OpenGL up to the last version that is supported by the platform.
Nothing like SDL or
no, that's the only way.
okay.
I mean, so far, unless somebody rolls up their sleeves and produce something meaningful from that.
Have you considered contributing to any of these libraries?
I've considered contributing. So the question was, shouldn't I contribute to some open source library to get something running out of this? Yes, I've actually considered contributing to Chrome Brew. There are a couple of outstanding bugs with Google that I filed with Google that need to be addressed first. One of them, one is a very funny bug. Their Wayland server neglects the virtual invert flag. So if I want, I mean, basically, in situations where I would like to invert the screen, because
OpenGL is right-handed and
exactly. So basically, everything that has an up-down orientation comes out the other way around when I do this.
You need to flip
I can flip it manually, no problem. I can fix this with the projection matrix, but I wouldn't like to do this at this day and age. So I've actually filed a bug with Google to fix their Wayland flag, and they've fixed it, and now I'm waiting for fix to get into the mainland.
Okay.
So once I have that fixed, I mean, once I have those things, there are a couple of more small things. Once they're fixed, I'll actually consider doing something with a Chrome Brew library that actually allows this for future generations.
Well, best of luck.
Thank you.
My question is, why would a game developer choose this way of developing games? Because as much as I understood, it works very well only on Android-based devices.
Sorry, which devices? I didn't catch that.
This works only for games. Works only on Android-based devices.
No. This is all Chrome OS devices that have support for Android applications, and this has been for all Chrome OS devices since version 68 to 70, depending on the device. So all Chromebooks that you can buy in the wild that have support for Chrome OS from version 68 to 70 and up, currently the latest one is 72, they all can do this. Any Chromebook that you can buy in the store for the cheapest. So that's the whole point. I mean, you don't really need a MacBook to get normal OpenGL on the go. Because, I mean, there's this dilemma. When you do development on the go, you want to go for the most expensive notebook because they usually give you the best battery life and the best performance. Now, in terms of performance, when you do development, you may not need the complete game running on your workstation. You may need just some bits and pieces, some editor running. You want to experiment with shaders and materials and geometries. You may not want to run the final product on your dev machine. Now, this is on one hand. On the other hand, you want the longest battery life that you can get out of your development environment, right? Out of your workstation and development environment. And those Chromebooks, they can really, really last for an entire workday, which is, you either need a very expensive laptop for that, I mean a notebook or a MacBook, something like this, or you can go with something as cheap as this. Now, the secret sauce in these devices is that they have extremely power efficient systems on a chip inside. So they are pretty much your cell phone put in a notebook, and they can last for days, which your notebook may or may not do, depending on how expensive it is.
So the game will not be operational system dependable?
The game will be, in most cases, operating system dependable, but I mean, when you do games, most games that run on game engines, they support...
Well, my question is because now Unity and Unreal Engine export pretty well for any much platform.
Yes, it is. Now, in order for Unity to start running on a Chromebook in native mode like this, somebody, like it was suggested already,
it's about the performance.
Has to do the porting of this thing to put this in a user library in a package manager like Chromebrew. So somebody who's doing Unity can actually take this and run Unity on top of that, because to run Unity needs basically OpenGL underneath. Unity can run on Linux, right? But this is work that needs to be done yet.
Just have one more question. Have you done something about supporting extensions, and is this going to be separate from what you're doing right now? OpenGL extensions.
The extensions are supported by the core. Basically, there is such thing which is called Android extensions for OpenGL, and Google mandates those extensions on every Android compatible device. And since this Chromebook giving Android support and compatibility, basically those extensions are mandated on the OpenGL implementation on Chrome OS as well.
Okay, yeah, they will be supported, but normally you go through something like...
Yes, I mean there is a simple procedure where you fetch the function address and you call it only then. I agree. Yeah, you're talking of an extension wrangler usually. I usually do those as I need them. I don't really use wranglers when I do code for my own. Yeah.
Okay, thank you very much for the questions. Thank you, Martin, for the presentation. Now I think more of my Chromebook.